Morning, everybody. I am Dr. Sunita Goyal, working as an associate professor in the Department of Applied Sciences and Humanities. In the engineering chemistry subject, we will discuss today the next part of stereochemistry. In this part, we'll discuss about the geometrical isomerism and chiral drugs. So, the contents will be different types of geometrical isomers like the cis and trans, and the new concept EZ nomenclature and chiral drugs. So, stereoisomerism is the phenomena which is exhibited by two or more compounds with the same molecular and structural formula, but different spatial arrangement of their atoms or groups will be there. This phenomena is known as stereoisomerism, and this can be categorized in two parts: the geometrical isomerism and optical isomerism. In our last video, we have already discussed the optical isomerism. Here, we will elaborate about geometrical isomerism. So, in geometrical isomerism, it arises when atoms or groups are arranged differently in space. And due to this difference in space about the carbon-carbon double bond in the molecule, there will be the restricted rotation about the carbon-carbon double bonds. Therefore, there will be the formation of cis and trans isomers. So, cis is that isomer in which the similar groups are placed on the adjacent positions of the compound. And trans is that isomer in which the similar groups are placed on the opposite side of the carbon-carbon double bond. Here, in these examples, we can see this is the carbon-carbon double bond in this molecule, and carboxylic acid molecules or carboxylic acid functional groups are present on the same side of the carbon-carbon double bond. Therefore, it is the cis isomers, and this is the trans isomer in which the carboxylic groups are present on the opposite side of the double bond. Similarly, in another example, 2-butene, the two methyl groups are present on the same side of the carbon-carbon double bond, therefore the cis, and here on the opposite side, the methyl groups are present, therefore the trans isomer. But now, we will discuss about a new type of notation or a new type of nomenclature. That is because there may be the cases where carbon-carbon double bond is there, but they are having 4 different types of atoms or groups. Like this, A, B, and C, D, all the 4 groups, or there may be 3 different groups are present on the carbon-carbon double bond. Then, how can we decide whether it will be cis or the trans isomer? So, for that, a new type of nomenclature is there, which is known as EZ notation or EZ system of nomenclature. For this, we will assign the priorities to the groups on the same carbon. So, suppose this is the carbon-carbon double bond, and at one carbon there will be 2 substituents on 2 opposite sides. We will assign the priorities to these groups. Well, one will be having the higher priority and the other will be having lower priority. Similarly, for the next carbon, if both the high priority groups are present on the same side of the carbon-carbon double bond, it is known as Z isomer. The Z comes from the German word zusammen, that means together. So both the same priorities are present on the same side of the carbon-carbon double bond, it is known as Z. It is the analogous to cis. And if the higher priority groups are present on the opposite side of the carbon-carbon double bond, it is known as E isomer. E comes from the German word antigegen, that means opposite. But the question arises here, how we can decide the priorities of the groups? That will be decided according to the sequence rules, or can in gold pre-log rules, which is also known as CIP rules. These sequence rules will be applied on a molecule to decide the priorities sequentially. Like first rule will be applied first If the first rule is ruled out, then the second rule will be applied, and so on. So as per the first sequence rule, the higher priority will be given to the atom of higher atomic number. But if the first rule is not applicable to decide the priority when it will happen, if the isotopes of the same element will be present. In that case, the atomic numbers will be same, but their atomic masses are different. So in case of isotopes, for example, deuterium isotope and protium isotope, the atomic numbers are same, 1, but the atomic masses are different. Deuterium has 2 atomic mass and protium has 1 atomic mass. Therefore, deuterium will be having the higher priority. Similar will be the case in case of carbon 13 and carbon 12. Carbon 13 will be having higher priority because of higher atomic mass. Now, the third rule is, if the priority is not decided by this rule because of the same element is present, so how can we compare these atoms? We will compare the next atoms till we get a first point of difference. So, the third rule will decide the priority. Similarly, if a functional group is doubly bonded or triply bonded, it will be considered equivalent to 2 or 3 such atoms like carbon oxygen means carbonyl group. That means carbon is bonded to oxygen 2 times. Similarly, if carbon is triply bonded with nitrogen, that means carbon is bonded to nitrogen 3 times. So it will be considered like that. Now we will apply these rules to some of the examples. Here, there is a carbon-carbon double bond. These 2 groups are present there. So we can assign priorities to these groups. Bromine is having the atomic number 35, while chlorine is having 17. So bromine will be having higher priority. While in both of them, we have to decide the priority. So carbon, and here hydrogen is attached to the carbon. So carbon is having atomic mass 12, while hydrogen is 1. Therefore, this will be having the higher priority. So higher priorities are present on the same side of the carbon-carbon double bond. Therefore, this is a Z isomer. But here, bromine and here methyl, both are having higher priorities. Therefore, and they are present oppositely to the carbon-carbon double bond. Therefore, this is E isomer. And similar is the case here. Nitrogen and oxygen. Oxygen is having atomic number 8, while nitrogen 7. So higher priority is OH. Similarly, as per the third sequence rule, both the same elements are present here. So carbon-carbon. But next to that, here hydrogen, 3 hydrogens are present. But here 2 hydrogens and 1 carbon is attached. Therefore, this group will be having higher priority. This is the same priorities are on the opposite side. Therefore, E isomer, and here it is the Z isomer. So this way we can assign E or Z notations. Now, the next topic of our video, that is the chiral drugs. We have already discussed that chirality is a property of an element which is non-superimposable with its mirror image. So, the drugs which are having such chirality, they are known as chiral drugs. A chiral molecule is a molecule which is having at least 1 asymmetric carbon. Carbon is not the only atom that can act as an asymmetric center. Sulfur, phosphorus, nitrogen, that can also work like a stereo center or the chiral centers. Therefore, they make the molecule chiral. In our pharmaceutical industries, we are having so many drugs, means the medicines, and these are the chiral molecules, which are their number is approximately 56%. And among them, 88% of them are in the form of racemates or the racemic mixture. That means they are present in their equimolar amounts of their enantiomers. Although the enantiomers of chiral drugs have the same chemical connectivity of atoms, but they show marked difference in their property like pharmacological property, toxicological property, pharmacokinetics, metabolism, etc. So many different types of properties they will be having on the human body or the organism body. So if we see in the natural compounds like amino acids, like sugars, we see that they are present in single enantiomeric form. They may be in the as L isomer or D isomer, as in the form of amino acids or carbohydrates, etc. The attachment of an enantiomer to the chiral receptor, this chiral receptor is present in the organism's body, is like a hand fitting into a glove. It is just like we cannot wear a left hand glove into the right hand. There is a special binding, or there is a special site for the left hand and the right hand glove. So the recognition of chiral drugs by specific receptor is explained by the scientists named Eason and Stedman as a three-point interaction of the drug with the receptor site, which is depicted in the next figure. Here we can see this is an enantiomer. This is here the carbon atom or any stereocenter is present. The A, B, C, and D, 4 different groups are attached to this stereocenter, and here is the drug binding site in the human body. We can see here that A is attached with A, B with B, and C with C, and D is remaining free there. So with this binding site, it is very much compatible to get attached. Therefore, we are saying it is an active enantiomer. And this enantiomer is having the non-superimposable mirror image. So it is having we are showing here a mirror plane which shows that it is making its mirror image. So its mirror image, it is another molecule, or but it is an enantiomer of the first one. Here we can see this is the mirror image of this. The C is here, and B and A, they have exchanged, C and A have exchanged their positions, because this is the laterally inverted figure, or laterally inverted molecule, or the mirror image. So if the binding site in the body is this A, B, and C, so C is not compatible with binding with A, because this is not having any compatibility, or the binding site with C. Similarly, this C will not be compatible with this A. So interlocking system will not be there. Therefore, we can say it is an inactive enantiomer. However, we can see the position after rotation. When we rotate it, then we can get this enantiomeric form. In this figure, D and A, they have exchanged their positions from the first one, but B and C are in the same position, but this D is not having the active site, but this D is not having the binding site with A, and this B and C is C, but B is B, yes, and A is free in this case. Therefore, this is also the enantiomeric form which will be inactive. So this is hypothetical interaction between the two enantiomers of a racemic drug with a receptor at the drug binding site. Here are some examples of chiral drugs whose enantiomers vary drastically in their properties. First example is thalidomide. Here we are having R and S forms of thalidomide. However, R is an effective sedative, and it has a soothing effect that relieves anxiety and makes the patient drowsy, while the S enantiomer is known to cause teratogenic birth defects. So they are very much different in their properties. However, their molecular formula and their chemical structure are same, but their spatial arrangement is different, or the arrangement in the space, three-dimensional space, is different. Therefore, their properties are very much different. The next case is about ibuprofen. These are the two isomers of ibuprofen. They are R and S. It is a well-known painkiller, ibuprofen. The enantiomer S, this one, it is having the desired pharmacological activity, while R is totally inactive. So we can see the difference in their properties due to their special arrangement in three-dimensional space. Another example is of carbon. As the human have the sensory organs, olfactory sensory organs, they are chiral in nature. These enantiomers of carbon, they smell differently to a human. So the R isomer is smell like a spearmint oil, while the S isomer smell like a caraway oil. So we can see a different property or the effects on the human body they are having as their enantiomers are different. So this is all in this video about this topic. You can get more information from the references. Thank you.